Hi everyone, Mr. Kwan here. Welcome back to part 2 of 30 integrals that will help you review for your Calculus 2 final exam. If you haven't watched part 1 of this video, I will link that in the description as well as on the screen. Also in the description, I will include a link to the PDF that contains all 30 integrals as well as hints to how to start the integrals and the final answers. If you are taking a Calculus 2 final exam soon, I wish you all the best of luck. Enjoy the video. As a quick reminder, here are those 30 integrals again, and in the last video we ended with question 17, and now we'll go ahead and start with question 18. Here we have the integral of the quantity 1 plus the square root of x to the 8th power dx. We're going to start off by using u substitution, and I'm going to let u equal 1 plus the square root of x. If we take the derivative here, we're going to end up getting that du is equal to 1/2 x to the negative 1/2 power dx. I'm going to rewrite this as 1 over 2 times the square root of x dx. So at this point we have du equals 1 over 2 root x dx. And in this equation, I'm going to multiply both sides by 2 root x. If we do that, we get 2 root x du is equal to dx. So now what I'm going to do is I'm going to rewrite my integral. I have u to the 8th power, and then dx is getting replaced with 2 root x times du. Now the problem arises that we have an x there and we want everything to be in terms of u. So what I can do from here is I can take my original definition of u and solve it for the square root of x. So if I subtract 1 on both sides, I end up getting the square root of x is equal to u minus 1. And now I can go ahead and plug that in to my integral. So we have, I'm going to factor out the 2, my constant, and then we have u to the 8th power, and the square root of x we can replace with u minus 1. Now I'm going to go ahead and distribute. So if we do that, we get u to the 9th power minus u to the 8th power du. Now I can take the antiderivative. So we get u to the 10th power over 10 minus u to the 9th power over 9 plus c. Let's go ahead and plug u back in. So we have 2 times 1 plus the square root of x to the 10th power over 10 minus 1 plus the square root of x to the 9th power over 9 plus c. And if we'd like, we can distribute that 2 in. So if I distribute the 2, that's going to give us a denominator of 5 in the first fraction, and then we'll have a 2 there. So here is our final answer for number 18. For number 19, we have the integral of 1 plus 12t all over 1 plus 3t and then times dt. So if you read the hints for this question, it says to use polynomial long division. And so I'm going to draw my little division bar. On the outside, I'm going to put 3t plus 1. And on the inside, or underneath my division bar, I'm going to put 12t plus 1. So the way that polynomial long division works is I want to ask myself, what am I multiplying to 3t in order to get 12t? So the value that makes that work is 4. So now I'm going to multiply 4 times 3t, which is 12t. And then I'm also going to multiply 4 times 1, which is 4. And then I'm going to line those up vertically and subtract. So 12t minus 12t is 0. 1 minus 4 is negative 3. And 0 minus 3 is just negative 3. So I can just drop the 0. So that negative 3 there represents my remainder. So what I can do is I can take my integral and rewrite it as the integral of 4 minus 3 over my original denominator, 3t plus 1 dt. From here, I'm going to break this up into 2 integrals. So I have the integral of 4 dt minus, and then in the second integral, I'm going to factor out the numerator of 3. On this second integral, I'm going to go ahead and use u substitution. I'm going to let u equal 3t plus 1. That's going to make du equal 3 dt. And if I divide both sides by 3, I get 1/3 du is equal to dt. So this ends up equaling, the antiderivative of 4 here is 4t, and then we have minus 3 times the integral of 1 over u, and then dt is getting replaced with 1/3 du. I think it'd be a little bit easier if I factored out the 1/3, so let's do that. Notice that the 3 divided by 3 in the front of the integral will become 1. So we get 4t minus the antiderivative of 1 over u is the natural log of the absolute value of u. And then we can add our constant of integration. Lastly, I want to plug back in and replace u. So we get 4t minus the natural log of the absolute value of 3t plus 1 plus our constant of integration. For question 20, we have the integral of 3x squared plus 1 all over x cubed plus x squared plus x plus 1 dx. Now, in the denominator, we have 4 terms, and sometimes when we have a 4-term polynomial, that indicates that we should try factoring by grouping. So in the first 2 terms, I have an x squared, and that's going to leave me with x plus 1. And in the second 2 terms, really I could just factor out a 1. And notice now we have an x plus 1 in both terms. And so because I have an x plus 1 here and an x plus 1 here, I can go ahead and factor that out. So I have x plus 1. And then what's going to be left over is this x squared plus 1. So now this becomes the integral of 3x squared plus 1 over x plus 1 times x squared plus 1 dx. And this looks like we would end up using partial fraction decomposition. So let's do that. We have 3x squared plus 1 over x plus 1 times x squared plus 1. And we want this to break up into 2 fractions. So my first fraction is capital A over x plus 1. Now, make sure you're careful for the second fraction, because the denominator of the second fraction is x squared plus 1, which is an irreducible quadratic, meaning that the numerator for this fraction would need to be something that is 1 degree less, and what that's going to look like is capital Bx plus capital C. So that's 1 degree less, and let's go ahead and get rid of these fractions, and I'm going to do that by using the method of clearing fractions by multiplying every fraction in this equation by the least common multiple of all of the denominators, which in this case is x plus 1 times x squared plus 1. So if I multiply that throughout, my first fraction will become 3x squared plus 1 equals capital A times x squared plus 1 plus capital B x plus C times x plus 1. From here, I can strategically pick values of x that's going to help us out, and one of those values is -1. So if we do that on the left-hand side of the equation, we get 3 times -1 squared plus 1. Now, notice that this entire term will become 0 because -1 plus 1 is 0. So let's see, 3 times -1 squared plus 1, that's going to end up being 4. And this all goes away, and then negative 1 squared is 1, plus 1 is 2, so we have 4 equals 2a, and if I divide both sides by 2, we end up getting a is equal to 2. So let's go ahead and replace that here. I'm going to put a equals 2, and now we need to solve for capital B and capital C. Now, because x squared plus 1 is an irreducible quadratic, I'm going to now rely on the method of comparing coefficients. You could plug in the strategic values, x values that involve complex numbers, but I'm just going to go ahead and use the method of comparing coefficients. So what we want to do now is I'm going to go ahead and distribute this 2 in. We get 2x squared plus 2, and then here I'm going to multiply that out. So we get bx squared plus bx plus cx plus c. Now we want to combine like terms on the right-hand side of the equation. So my quadratic terms are 2x squared plus bx squared. I'm going to go ahead and factor out the x squared, so that will leave us with 2 plus b x squared, plus my two linear terms are bx plus cx. So I'm just gonna, we have 2x squared, bx squared, and then here are our two linear terms. And I'm gonna factor out x, so we have b plus c times x, and then our two constant terms are 2 and c. So then I'm going to put plus c plus 2, like that. And then here, on the left-hand side, we have 3x squared, and if it helps you, we could put plus 0x plus 1, and now we're going to go and compare coefficients. So I've highlighted the corresponding coefficients on each side of the equation, and so the yellow, it ends up giving us the equation b plus 2 is equal to 3, and then I'm going to move over to the green, or the constants, and that's going to tell me that c plus 2 is equal to 1. Solving both of these gives us capital B is equal to 1, and capital C is equal to negative 1. Alright, so based off the numerators that we found in our partial fraction decomposition, this is what our integral is going to turn into. From here, I'm going to break this up into more integrals. So the first integral, I can factor out a 2 from the numerator outside of my integral, and that will leave me with 1 over x plus 1 dx in the integrand. And then this second integral here, what I'm going to do is I'm going to break this up into 2 fractions and consequently 2 different integrals. So my first integral would be x over x squared minus 1 dx. And then my next integral would be minus the integral of 1 over x squared. This should be a plus 1, so x squared plus 1 dx. In this middle integral here, I'm going to use u substitution by letting u equal x squared plus 1. du is going to end up equaling 2x dx, and then if I divide both sides by 2, we get 1/2 du is equal to x dx. And so from there, we're going to get 1/2 times the integral of 1 over u du, which gives us 1/2 times the natural log of the absolute value of u. I'm just going to go ahead and sub that back in. And then plus our constant of integration, I can maybe just put plus c2. And then this integral here is going to end up being 2 times the natural log of the absolute value of x plus 1 plus some other constant. And then this integral here, 1 over x squared plus 1, that should look familiar. So the antiderivative of that is arctangent or tangent inverse of x. and then we could put another constant of integration. What's going to end up happening is when I combine all of these, I'm going to have a constant, another constant, another constant. So I'm just going to combine all of those into one general constant that I'm going to call capital C. So let's go ahead and combine all of these. We're going to end up getting 2 times the natural log of the absolute value of x plus 1 plus 1/2 times the natural log of the absolute value of x squared plus 1 minus tangent inverse of x plus c. Now, one thing that you'll notice, for example, in the final answers is that this term here, the inside of the natural log is x squared plus 1, which is always going to be a positive number. And so we end up dropping the absolute value bars and write it like this. So whether you leave it like that, or leave the absolute value bars or parentheses, that's fine. So here is our final answer. For question 21, we have the integral of 1 over 1 plus e to the x dx. Let's go ahead and use u substitution, and we're going to let u equal 1 plus e to the x. Then that means that du is going to equal e to the x times dx. If I divide both sides of that equation by e to the x, we get du over e to the x is equal to dx. Now, if I rewrite my integral, I have 1 over u, and dx is getting replaced with du over e to the x. And again, we don't want x in our integral, so what I'm going to do here is from my original u value, I'm going to solve for e to the x by subtracting 1 on both sides, and we get e to the x is equal to u minus 1. What that's going to allow us to do is now we'll have 1 over u times du over u minus 1. And I'm going to write this slightly differently. So this is equal to 1 over u times u minus 1 du, like that. So from here, you look at this and hopefully you recognize that we want to use partial fraction decomposition. So I have 1 over u times u minus 1, and I want to rewrite this as capital A over u plus capital B over u minus 1. And I'm going to clear fractions by multiplying by the least common multiple of all of my denominators. So I'm going to multiply every fraction by u times u minus 1. And the resulting equation will become 1 equals a times u minus 1 plus b times u. And from here, we can choose strategic values for u. So the first u value I'm going to choose is 0, and that will give us 1 equals capital A times 0 minus 1, and then plus b times 0, and that's going to become 0. And we get negative a is equal to 1, or a is equal to negative 1. In this scenario, we're going to let u equal 1. This is going to become 0, and we get b is equal to 1. So we end up getting that 1 over u times u minus 1 is equal to negative 1 over u plus 1 over u minus 1. So now we're at this point, I've gone ahead and taken that integral and broken it up, and now we can start to integrate. So this is going to end up being negative natural log of the absolute value of u plus the natural log of the absolute value of u minus 1 plus our constant of integration. From earlier, we defined u to be 1 plus e to the x. So let's go ahead and plug that in, we have the negative natural log of the absolute value of 1 plus e to the x plus the natural log of the absolute value of 1 plus e to the x minus 1 plus c. Now, a couple of notes. 1 plus e to the x is going to be a positive number, so if you'd like, you can drop the absolute value bars, and we can make this negative natural log of 1 plus e to the x. What's going to happen in our second natural log is 1 and minus 1 will become 0, so we'll have the natural log of e to the x, and that is just equal to x. And if you don't want the negative in the front, we can rewrite this as x minus the natural log of 1 plus e to the x plus our constant of integration. And here's our final answer. For question 22, we have the integral of sine of the square root of a times t dt, where a is just some constant here. And we're going to end up using u substitution. I'm going to let u equal the inside of our trig function, which is the square root of a times t. Then I want to take the derivative. It might be helpful to rewrite this as a times t to the 1/2 power. So when I'm taking the derivative, I would use power rule. So we have 1/2 times a times t to the negative 1/2 power. And now we need to use chain rule. So I'm going to take the derivative of the inner function, which is going to be a, and then we should have dt after that. So I'm going to clean this up a bit. Because I have a negative exponent and it's the negative 1/2 power, I can move that into the denominator. So that's going to be 1 over 2 times the square root of a times t. And then I still have an a, so maybe I'll put that in the numerator and then dt like that. Okay, so at this stage we have du is equal to a over 2 times the square root of at dt, and I'm going to solve this equation for dt. So I'm going to multiply both sides by 2 times the square root of at. I'm also going to divide both sides by a. Okay, so coming back to my original integral, we have the integral of sine of u dt is getting replaced with this expression here. So I have 2 times the square root of at over a times du. Now I do not want t because we're integrating with respect to u. Notice that in our original definition we defined u to be equal to the square root of at. And so here we can replace that with u. Also, another thing to note is, remember, a is a constant with respect to our integral. So I'm going to factor out 2 over a outside of my integral. And then what we're going to be left with is sine of u times u du. And if I reorder that, it's going to be u times sine of u du. Now, looking at this integral, hopefully you recognize that we would want to use integration by parts, and we can use the more traditional integration by parts. I'm going to go ahead and utilize tabular method. If you don't know what tabular method is, please go and watch my video series on integration by parts. So here I'm going to put the thing that I want to differentiate, and then in this column I'm going to put the thing that I want to integrate. So the derivative column, I have u, then the derivative of that is 1, and then the derivative of that is 0. Now for this column I have sine of u. The antiderivative of that is negative cosine of u, and then the antiderivative of that is negative sine of u. and then I want to connect these across diagonally, and I'm going to put a plus sign and a minus sign here. So coming back to our integral, we have 2 over a times, if I multiply across the diagonals, and then we have positive u times negative cosine of u. That's going to be negative u cosine of u. And then here what's going to happen is these negatives will end up multiplying to become positive, so I'm going to put plus sine of u and then plus our constant of integration. Let's go ahead and plug back u. So we have 2 over a times negative square root of a times t times cosine of the square root of a times t plus sine of the square root of a times t plus our constant of integration. And if you'd like, you could also distribute in the 2 over a. If we do that, we get negative 2 over a times the square root of a times t times cosine of root a t plus 2 over a sine of root a t plus our constant of integration. And there's our final answer. For question 23, we have the integral of the natural log of x plus the square root of x squared minus 1 dx. In this question, we're going to end up using integration by parts. I'm going to go ahead and let u equal the natural log of x plus the square root of x squared minus 1. And then let's go ahead and take the derivative now. So I have 1 over x plus the square root of x squared minus 1. And then I need to multiply that, because we're going to use chain rule, by the derivative of the inside of our natural log. So I have 1 plus, then we have 1/2 x squared minus 1 to the negative 1/2 power, and then I also need to multiply that by the derivative of the inside or inner function, which the derivative of x squared minus 1 would be 2x. Notice that I have a 2 in the denominator as well as a 2 in the numerator, and those are going to end up canceling out. And also, this expression with the negative exponent, I can move that into the denominator. So I'm going to go ahead and rewrite this expression here as x over the square root of x squared minus 1. Also, inside here, if I wanted to find a common denominator for those two values, then the 1 I could multiply by the square root of x squared minus 1 over the square root of x squared minus 1. So let's go ahead and do that. So now that I've changed that 1 by multiplying by the square root of x squared minus 1 in both the numerator and the denominator, notice that inside the parentheses, these two fractions have the same denominator, so I can also combine that into a single fraction. And if I do that, I also need to put dx at the end, so let me go ahead and combine those two fractions. Okay, so I went ahead and did some more simplification. Notice what's going to happen now is these terms are going to cancel out because I have 1 in the numerator and I have 1 in the denominator. So finally we'll get du is equal to 1 over the square root of x squared minus 1 dx. So there's a lot of algebra there to get that. Now let's go ahead and find dv and v. So the only thing remaining in the integral, because we set u equal to the natural log, dv is going to equal dx, and if we integrate, we end up getting v is equal to x. So let's go ahead and put all of that together now using our mnemonic device, which is ultraviolet super voodoo. So u is equal to the natural log of x plus the square root of x squared minus 1. And then v is x, so I'm going to put that in the front there, minus the integral of v du. So du is 1 over the square root of x squared minus 1 dx. And if I multiply those together, then my numerator here becomes x. All right, so in order to evaluate this integral right here, I'm going to use substitution. I'm going to use w substitution since I used u earlier, so why don't we use the variable w? And I'm going to let w equal the thing underneath the square root, and that's going to imply that dw is equal to 2x dx. And then if I divide both sides by 2, we get 1/2 dw is equal to x times dx. All right, so now let's take this and we're going to have 1/2 times the integral. X times dx is getting replaced with dw times 1/2, and I factored out the 1/2 outside of my integral. So I'm going to have 1 over, and then we'll have the square root of w, dw. Now I'm going to rewrite this as w to the negative 1/2 power. And that is equal to 1/2 times, I'm going to increase the power by 1, so that's going to give me positive 1/2. And then if I divide by 1/2, that's the same thing as multiplying by 2. These 2's will cancel out, and I'm going to go ahead and plug w back in. So we have the square root of x squared minus 1 plus c. So putting this all together now, we have our answer is x times the natural log of x plus the square root of x squared minus 1 minus the expression that we just calculated, which is the square root of x squared minus 1 plus our constant of integration here. And there is our final answer. In question 24, we have the definite integral from -1 to 2 of the absolute value of e to the x minus 1 dx. Now, what I want to do is I want to start off by graphing y equals e to the x, and that's going to look something like that. So if we were to shift this down 1 unit, what's going to happen is the new y-intercept will be at the origin. So here's a quick sketch of y equals e to the x minus 1. Now, when we take the absolute value of a function, what that does is any part of the function's graph that falls below the x-axis, it gets reflected over the x-axis so that all parts of the graph are on or above the x-axis. So what's going to end up happening for this portion of the graph is it's going to get reflected if I were to look at the graph of y equals the absolute value of e to the x minus 1. And so what we need to do then is when we're thinking about calculating this integral, we need to break it up so that the first integral runs from -1 to 0, because everything after 0, the function's output is positive. And so here, if I'm integrating e to the x minus 1 dx from -1 to 0, that output is going to be a negative number, and we want to make it positive by multiplying by -1. Then we can add on the definite integral from 0 to 2 of e to the x minus 1 dx. So if we start to take the antiderivative, we're going to have negative e to the x minus x, and this is being evaluated from x equals -1 to x equals 0, plus e to the x minus x, evaluated from x equals 0 to x equals 2. Let's go ahead and plug in those numbers. So I have negative e to the 0 minus 0 minus e to the negative 1 minus negative 1, which will become plus 1, plus e squared minus 2 minus e to the 0 minus 0. So if we do some simplification here, we have negative 1 minus, I'm going to write this as 1 over e, minus 1. I went ahead and I distributed in the negative signs, plus e squared minus 2. That is minus 1, and then minus 0. Those will cancel out. If I distribute in the negative sign, then as a final answer, we should get e squared plus 1 over e, and then these will combine into minus 3. So here's our final answer for number 24. For question 25, we have the integral of 1 plus sine of x over 1 plus cosine of x dx. And I'm going to approach this question by multiplying both the numerator and the denominator of our integrand by 1 minus cosine of x. The reason that I'm doing that is because in the denominator, if we multiply that out, our new denominator is going to end up being 1 minus cosine squared x, and I'm going to be able to use the Pythagorean identity on that in a little bit. I'm also, in the pink, I'm multiplying by 1 minus cosine of x over 1 minus cosine of x, and algebraically we're allowed to do that because that is equivalent to 1. If I multiply out the numerators, I have 1 minus cosine of x plus sine of x minus sine of x cosine of x dx. Now what I'm going to do is I'm going to rewrite 1 minus cosine squared as sine squared x using the Pythagorean identity. And from here, what I'm going to do is I'm going to break this up into 4 different integrals because in the numerator, we have 4 terms. So I can break this up into different fractions. So I'm going to do that really quickly. So I've gone ahead and I've separated this into 4 different integrals. And some of these we can rewrite so that they will be easier to integrate. The first one, 1 over sine squared x, is equivalent to cosecant squared x. And our third integral, notice that there is a sign in both the numerator and the denominator. And so those will divide out. I'll have 1 over sine, which is equivalent to cosecant x. And in our last integral, we also have both a sign in the numerator and in the denominator. So those will divide out and leave us with cosine of x over sine of x. So in this second integral here, the way that we're going to go about integrating that is by u substitution and letting u equal sine of x, which will make du equal cosine of x dx. So that integral will change into 1 over u squared du, and that's going to end up being negative 1 over u plus our constant of integration. And then I can plug u back in. And what's going to happen is this minus and this minus will end up changing that into a plus in the end. Let's see what else we can integrate. In this last integral, we're also going to use u substitution by letting u equal sine of x. And then du will equal cosine of x dx. So that's going to become the integral of 1 over u du. And that's going to give us the natural log of the absolute value of u plus c4. And then we could say that that's equal to the natural log of sine of x plus some constant. Okay, let's clean this up. So our first integral, cosecant squared x, its antiderivative is negative cotangent of x. And then we have plus 1 over sine of x. And our third integral, if we're integrating cosecant x, that ends up being the natural log of the absolute value. This should be a minus sign. So minus the natural log of the absolute value of cosecant x plus cotangent x. And then we have minus the natural log of the absolute value of sine of x, and then we have our constant of integration. And here is our final answer. For number 26, we have the integral of the natural log of x quantity squared dx. I'm going to use integration by parts, and I'm going to let u equal the natural log of x quantity squared. If we take the derivative, we get 2 times the natural log of x, and then I'm going to multiply by the derivative of the inner function, which is 1 over x. So I'm going to put that 1 over x there, and then dx. Our dv value is dx, and then if we integrate, we get v equals x. So putting this together, we have x times the natural log of x, that's squared, minus the integral of v du. What's going to happen is the x in the numerator and the x in the denominator will cancel out, and we'll have 2 times the natural log of x dx. I'm going to factor out the 2 outside of my integral. Now, to integrate the natural log of x, I'm going to use integration by parts again. I'm going to let u equal the natural log of x, then du will equal 1 over x dx. dv, I'm going to let equal dx, and then v will equal x. So we have x times the natural log of x quantity squared minus 2 times x natural log of x minus the integral of v times du. That's going to leave us with 1 dx. I'm going to go ahead and distribute in the 2. So we have minus 2x natural log of x. And then if I were to integrate 1 dx, that would give me x. So it looks like if I distribute that negative 2, it would give us plus 2x plus our constant of integration. And here's our final answer for number 26. For question 27, we have the integral of x cubed times e to the x dx. Now you can use the more traditional integration by parts. I'm going to use the tabular method. I think it's going to make life a lot easier. So the thing that we are differentiating is x cubed. Its derivative is 3x squared, then 6x, then 6, then 0. Luckily, e to the x, if we integrate that, it is going to continue being e to the x. I'm going to draw my diagonal lines, and then along these diagonal lines, I will alternate plus or minus. So this is going to end up equaling x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 times e to the x plus our constant of integration. And there's our final answer for number 27. For number 28, we have the integral of e to the power of cosine of t times sine of t dt. Let's go ahead and use u substitution. I'm going to let u equal cosine of t. If we take the derivative, we'll get du equals negative sine of t dt. And multiplying both sides by -1 gives us negative du is equal to sine of t times dt. So if we rewrite our integral, we have e to the power of u, and then sine of t dt is getting replaced with negative du. I'm going to factor out that negative sign. And then that's going to equal negative e to the power of u plus our constant of integration. And then if we replace u, we'll have negative e to the power of cosine of t plus our constant of integration. So here is our final answer for number 28. For number 29, we have the integral of sine of the natural log of x all over x dx. I'm going to use u substitution by setting u equal to the natural log of x. Du is going to equal 1 over x dx. So rewriting our integral, we have the integral of sine of u, and then 1 over x dx is getting replaced with du. If we integrate that, that's going to end up giving us negative cosine of u plus our constant of integration, and then we have negative cosine of the natural log of x plus our constant of integration. And here's our final answer for number 29. For number 30, we have the integral of sine squared t times cosine to the 4th of t dt. And I'm going to rewrite this as sine squared t times cosine squared t times cosine squared t dt. And what that's going to allow me to do is, in these first two terms here, I'm going to combine that into sine of t times cosine of t quantity squared. And then we still have the remaining cosine squared t dt. From here, what I can do is I can rewrite the thing inside of the parentheses using the double angle identity for sine. So we would get this quantity, and then cosine squared t I'm going to rewrite using the power lowering identity. So this is going to be times 1/2 1 plus cosine of 2t, and then we have dt at the end. Now, if I square this thing, that's going to end up being sine squared 2t over 4, and I'm going to factor out 1 over 4 times 2. That's going to give me 1/8, and then what's going to be remaining is sine squared 2t times 1 plus cosine of 2t dt. From here, I'm going to distribute the sine squared in. So I've gone ahead and I've distributed it in sine squared of 2t, and we get this integrand. And now I'm going to split this up into two integrals. For this second integral here, I'm going to use u substitution by letting u equal sine of 2t. If we take the derivative, we get du equals 2 times cosine of 2t dt. And dividing both sides by 2 gives us 1/2 du equals cosine of 2t times dt. So we're going to end up having 1/8 times 1/2 times the integral of u squared and then du. So that's going to be 1 over 16 times u cubed over 3 plus our constant of integration, and 16 times 3 is 48. And if I plug u back in, we get sine cubed of 2t over 48 plus our constant of integration. Now in this integral here, I'm going to use u substitution as well by letting u equal 2t. Then du is going to equal 2 times dt, and dividing both sides by 2, we get 1/2 du is equal to dt. So then we'll have 1/8 times 1/2 times the integral of sine squared u du. So 1/8 times 1/2 is going to give us 1/16, and in order to integrate sine squared u du, I'm going to use the power lowering formula, and so that's going to give us 1/2 times 1 minus cosine of 2u du. I'm going to factor out the 1/2, so that will give us 1/32 times the integral of 1 minus cosine of 2u du. So that's going to give us 1/32 times u minus 1/2 sine of 2u plus some constant of integration. I'll just call that C1. And from here, we can go ahead and replace u with 2t from earlier. So that's going to give us 4t inside here. And then I'm going to also distribute in the 1/32, so that's going to be t over 16 minus 1/64 sine of 4t plus some constant. So combining the two parts, we have that our final answer is t over 16 minus sine of 4t over 64 plus sine cubed 2t over 48 plus our constant of integration. That concludes this video on 30 integrals to help you ace your Calculus 2 final exam. Thank you so much for watching this video, and we'll see you next time.